Hello, welcome to the first set of notes of differential equations. This first set of notes is going to focus on definitions and terminology. It's a lot of background. What is a differential equation? How do we classify differential equations? What are we going to be doing in this course? What are our goals? What are solutions going to look like? So it's going to be a little dry, just to forewarn you, because it's going to be a lot of definitions, not a whole lot of what we typically think of as math. So with that being said, let's just jump right in. Of course, the first question is going to be, what is a differential equation? So that's what we're going to start with, definition. Differential equation is an equation that contains derivatives or differentials of one or more dependent variables with respect to one or more independent variables. So first thing that we're going to do is we are going to learn how to classify differential equations. And so we classify differential equations by these three things you see: type, order, and whether or not the equation is linear. So if we look at type, there's two different types. There's an ordinary differential equation, and then there's a partial differential equation. So an ordinary differential equation has ordinary derivatives with respect to a single independent variable. So some examples. One that you may have seen before, something like dy dx is equal to negative x over y squared. That has ordinary derivatives. Another one, we might have something like y double prime subtract 2y prime add 4y is equal to 0. That y double prime is just another way of writing the second derivative of y with respect to x. Okay, another one, we might see y subtract x dx add 4x dy is equal to 0. So those are all examples of ordinary differential equations. Now a partial differential equation, as you can probably guess, is going to have partial derivatives. So some examples, we might have the partial of u with respect to y is equal to negative the partial of v with respect to x. Or we might have the second partial of u with respect to x add the second partial of t with respect to y is equal to 0. So that's the first way that you are going to classify differential equations. Do they have ordinary derivatives only, or are there also partial derivatives? So after you classify by type, oftentimes we look at order. When we say the order of an equation, we are referring to the order of the highest derivative. So for example, we might have second derivative of y with respect to x, add 3 dy dx to the fifth, subtract 4y is equal to x. Okay, so what we're looking for here is the highest derivative, which is this right here. This fifth power does not affect the order. So if we were to classify this equation, first of all, we know it's an ordinary differential equation because it doesn't have any partial derivatives. And we also know that it's second order because of this second order derivative. So in general, a general nth order differential equation can be represented by, it's a function of x, y, dy dx, second derivative of y with respect to x, all the way up to the nth derivative of y with respect to x equals 0. Now, this doesn't mean that the equation is going to have all of these components, right? It's definitely going to have this one because we're talking about nth order. Might have x, dy dx, might be missing some of the ones in between, but it'll definitely have this nth order. So those are the first two classifications, type and order. The last thing that we're going to be interested in is whether or not the equation is linear. So taking a look at a linear example. So we have an of x times the nth derivative of y with respect to x plus an minus 1 of x, the n minus 1 derivative of y with respect to x, all the way down to a1 of x dy dx, add a0 of x times y equals g of x. Okay, so what makes this linear? Well, there's two conditions here that we see. The first thing that we see is all of our coefficients are in terms of x. So in order for an equation to be linear, we need coefficients in terms of x. Second condition, if we think back to algebra 1, what made an equation linear? In algebra 1, an equation was linear because every x or every y, every variable was to the first power. So in this case, in this case, looking at all of our derivatives, they are all to the first power. So the second necessary condition is that y and all its derivatives are to the first power. Okay, any other equation would be nonlinear. So any other equation that does not meet those two requirements is going to be nonlinear. So if we go back to this example from above, our order example, this one is nonlinear. So I'm just going to copy it again. Second derivative of y with respect to x, add 3 dy dx to the fifth, subtract 4y is equal to x. Okay, so our coefficients are in terms of x. So if we check that, we have a coefficient of 1, a coefficient of 3, a coefficient of -4. Then though, when we check our derivatives, we see this derivative is to the fifth power, which makes this equation nonlinear. Okay, so let's take a look at our first example, which has to do with classifying. So we have two equations, and we are going to classify them by order, type, and whether or not they are linear. Okay, so the first thing that I'm going to notice is my highest derivative is a third derivative, so this is third order. Then I notice they're all ordinary derivatives. I don't have any partials, so this is an ordinary differential equation. And then, if I check my linear qualifications above, my coefficients are in terms of x. All of my derivatives and y is to the first power, which makes this linear. Okay, if I go to my second question, if I classify by order, I have a second derivative here. So this is going to be second order. I notice these are partial derivatives, so it's going to be a partial differential equation. And then because we have a derivative to the second power, this is going to be nonlinear. Okay, so at this point you might be wondering, is this important? How important is it to be able to classify, and why? So in order to answer that, we're going to move to the next page and talk about our two goals for this course. The first goal is we want to be able to find differential equations that model physical situations. So this again is going to relate back to physics. And then we're going to find solutions of differential equations. Now we are going to focus on ordinary differential equations. We might take a look at some partial, but mostly we're going to be focusing on ordinary. We are going to learn many different ways of solving equations that are going to be dependent on the equation type. And so it's going to be very important that you can recognize a linear ordinary equation, because that is going to require one solving type versus nonlinear, which are going to require different types. So now that we know how to classify these equations, the next thing that we're going to take a look at is what it means to be a solution of a differential equation. And in the objective, you can see we're going to talk about implicit and explicit solutions. So definition, a function f defined on some interval I, which when substituted into a differential equation, reduces the equation to an identity, is a solution of the equation on that interval. Okay, so we're going to see an example here. Example 2, verify that y equals this function satisfies this differential equation for all x greater than 0. Okay, so what we're going to end up having to do is we're going to have to substitute this y into our differential equation. So we're going to notice in our differential equation, we have y, we also have the second derivative of y, which tells us we're going to need to find the second derivative. So if I start with finding the first derivative of y, I get x to the negative 1/2 rather, subtract 1/2 x to the negative 1/2 natural log of x, subtract x to the 1/2 times 1 over x. So remember, here you're going to have to do the product rule. Okay, so if I simplify that, then it gives me 1 over root x, subtract natural log of x over 2 root x, subtract 1 over root x. So that is kind of nice here. So our first derivative ends up being negative natural log of x over 2 root x. And because I'm finding the second derivative, I'm going to express this as negative 1/2 x to the negative 1/2 natural log of x, just because that's going to make it easier for me to do the product rule. So now my second derivative, I have 1/4 x to the negative 3 over 2 natural log of x, subtract 1/2 x to the negative 1/2 times 1 over x. So that gives me 1/4 x to the negative 3 over 2 natural log of x, subtract 1/2 x to the negative 3 over 2. So all of that is the background that we can now then substitute into our equation. So now we're going to end up with 4x squared, second derivative of y, so 1/4 x to the negative 3 over 2 natural log of x, subtract 1/2 x to the negative 3 over 2, add y is just our original function, so that's 2x to the 1/2, subtract x to the negative 1/2 natural log of x, and I ran out of room. We want to see, does this equal 0? Okay, so I'm going to have some distributing to do. So I end up with x to the 1/2 natural log of x, subtract 2 x to the 1/2, and then I have 2x to the 1/2, subtract x to the 1/2 natural log of x, which does in fact equal 0. So we have verified, we have shown that the function we have, that y equals, is in fact a solution of this equation for x is greater than 0. And we are requiring that x is greater than 0 because of this natural log. Okay, so let's keep going then. One thing for you to know is that not all differential equations have solutions. So for example, if I take y prime squared, add y squared is equal to negative 1. This is not going to have a solution. And we should be able to tell that just by looking at it. We have a squared quantity, which is positive. We're adding another positive quantity, and we're getting a negative number. That's not going to have a solution. Now, what if instead we take that equation and change it to a 0 instead of a negative 1? Is that going to have a solution? Well, this one you might be able to figure out just by looking at it. Our solution is y equals 0. And this is what we call a trivial solution, because it can be found by inspection. In this class, that's not what we're interested in. So we're not going to be interested in trivial solutions. We're going to be interested in ones that are general solutions, what we call general. And we'll get into that more as we go on. Next thing to talk about is the difference between an implicit and an explicit solution. So an explicit solution is if in the form y equals f of x. So it's going to be a solution or a function in terms of one variable. An implicit solution, on the other hand, is going to be a function of a few variables set equal to 0 oftentimes. So let's take a look at example 3 where we have an implicit solution. So we are going to show that x squared add y squared add c equals 0 is an implicit solution of that equation. First thing we're going to have to do is we're going to have to find a derivative because we need dy dx. So we're going to take that x squared add y squared add c equals 0, and we're going to take the derivative with respect to x. So we're going to have some implicit differentiation there. So when we do that, we get 2x add 2y dy dx is equal to 0, which gives us dy dx is equal to negative x over y. If we substitute that into our equation, our dy dx is negative x over y. So we get negative x over y is equal to negative x over y. Hence, yes, we have a solution. Okay, sometimes you'll take an implicit solution like this and you'll be able to make it explicit. You'll be able to kindly solve for y. In this case, we could. Sometimes that's not going to be possible. We look for explicit solutions if we can. So that is a lot of the background of what you needed to know for this first set, but there are some remarks that we're going to end with. And by some, I mean quite a few. Okay, first one, the number of solutions for a differential equation is typically infinite. Typically infinite. So that last equation that you saw contained a plus c, right? And so there are infinite solutions based on what the value of c is. Next remark, solving a first-order differential equation usually yields a family of curves such like g of x, y, c is equal to 0 as a solution. If you're solving an nth order differential equation, you can expect a family of the form g of x, y, c1, c2, all the way up to c of n equals 0. And I didn't give us a lot of room to write this, but these parameters, that's called an n-parameter family. Okay, a solution that is free of arbitrary parameters is called a particular solution. Okay, so for example, this right here is a general solution because it has that parameter c. But if c is 1, we get the solution y equals e to the x. Y equals e to the x then is an example of a particular solution because it does not have any arbitrary parameters. Sometimes a differential equation has a solution that cannot be obtained by specializing the parameters in a family of solutions. This is called a singular solution. So for example, we have this differential equation here. Y prime is equal to xy to the 1/2. The family of solutions, and we'll know how to solve this eventually, is y equals 1/4 x squared plus c squared. Now, that being said, y equals 0 is also a solution. And you can verify that by plugging it into the equation. But what you will notice is that y equals 0 cannot be obtained from here. There's no value of c that we can put in to make this turn into y equals 0. So this is called a singular solution. Okay. 2 remarks remaining. So the last one is the difference between a function and a solution. Okay, so if we are looking at y equals 1 over x, we say that this is a function where our domain is all real numbers except x cannot be 0. Now, we can also refer to this y equals 1 over x as a solution. And so this y is equal to 1 over x is a solution to the differential equation, for example, x, y prime, add y is equal to 0. And that is a solution on any interval not containing 0. So it's very important that we differentiate between when we are talking about a function in general and when we care about that function in relation to a differential equation. And lastly is just something for you to recall from Calc 1. If we have this f of x and we are looking for f prime of x, a lot of people know, okay, I'm going to plug my 2x in and they get e to the 2x. What you have to remember though is you got to multiply by the derivative of 2x. So that's just something that you're going to need moving forward. Okay, thank you for sticking with me through this background. What we're going to be looking at next class is some more background. What our solution is going to look like. We're going to look at what's called an initial value problem, and then we'll get into some models after that. See you next time.